Welcome to this screencast about our last data structure that we're going to talk about in ICS 211. Today we're talking about hash tables. The goals of a hash table are to access an item based upon its key. Its key could be its own self, but we don't want to have to search for that key in something. We want to very quickly access the item by a constant time. So we want a big O of 1 for the access to an item in this hash table or this data structure. Now, if you recall that if we had a list, to access any one item, to find that item in the list is a big O of n, because you got to search the list for it. You know, the index of is a big O of n operation. For a tree, a binary tree, if it's a search tree, you have a log n because you go left or right, you divide the problem in half each time, but that's still big O of log n, which is a lot bigger than constant time. So the goal is to create a data structure that we can get to the items in the structure with a constant time, big O of 1. So how do we do this? We need to map something about the key into an index into the table. One way is to create a hash code, which is take the key and produce an integer from the key, hashing it. And then if you take the hash code calculation and then we mod it by the table size, remember modulus goes from 0 to n minus 1, where table size is n, that will give us an index into our table. So that's a hash code should, if that's a big O of 1 operation, mod is a big O of 1 operation. We'll get to 2 and we'll be in the place and we can find our object very quickly. But what if the hash code gives you the same answer for 2 different keys? We have to then resolve what they call collision, is when the hash code calculation mod the table size produces the same index. Now you can get that a whole bunch of ways. Hash code calculations might give you the same value. The other way is if the table size is small, you can get the same hash code, or you can get the same mod, and then we'd have a collision. So we have to resolve the collisions, and there's several ways that we do this. So let's talk about collisions a little more. Many times there's more hash codes than table size. I mean, you're not going to have a table size that is the size of int. It's just, you don't have that big of a table. You don't have that much memory. So the great example is, let's say we're going to use the Unicode value for the character, mod it by a table size of 200. If we have right parentheses and a small letter n with a tilde, they both mod, they get the same index, even though they have different hash codes or using their Unicode, and they would have a collision into our table at index 41. So we need to resolve that index, get to the same index. So we got to figure out a way to resolve that collision. But we also have to figure out how to calculate this hash code. We want to have this hash code calculation to give us a random distribution. We don't want them to all come at 1. If the calculation returns a 1 for every possible thing, that's bad. We want to actually have it give us a nice random distribution of all possible values of the hash code. We also want to have 2 different keys to try and generate a different hash code. For example, if we just use a simple algorithm of adding each individual piece of the key, and we have a sign and sing, if we sum the int values of the characters, there's no concept, sign and sing have the same letters, so if we just add up their int values, we'll get the same value. There's no acknowledgement of position of the letter in the key, which would give us a different value. So one way to do that is to not use a simple addition, but let's multiply the value of letter 0 by a prime number raised to the n minus 1 plus the next letter, all to 31 to minus 2, and all the way down we just add the last value, the value for the last letter. So what that does is that makes the position of the values in the key has a different value, so that now sign and sing do provide or create different hash codes. And using a prime number like 31, when you multiply it and add it up, that tends to generate relatively few collisions, and it also tends to distribute the numbers across the total values of your hash code, across all the integer values. So this is often the algorithm that you'll see is used by Java to calculate hash codes. If you use Eclipse and you have it automatically generate the hash code, you'll see that it uses this same formula to create the hash code for your class. Another thing to think about, String.hashCode cannot be unique. There's only so many integers. Integers can only represent so many values, and there are many, 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 many more strings, possible strings, than those values. However, the algorithm that we're using, that hashcode algorithm, will distribute the values fairly evenly over the range of ints. Now, recall that hashcode returns an int. An int is a signed integer, so it can return a negative value. That's why we need to add the math abs to string hashcode or any hashcode, because we don't want that negative. If you take a negative number and mod it by the table length, you get a negative index, and you can't access a negative index into the table. So we need to take an absolute value. Now we could do the math abs around the whole thing, or we could just do it on the hash code. That doesn't really change the probability of collision, because of the hash code spreads it out over the range of ints. Now the probability collision with this particular algorithm is proportional to how full the table is. If there's nothing in the table, there's no collisions. If there's one thing in the table and the table length is 1, then you got a guaranteed collision. If the table length is 1,000,000, then you have 1 in 1,000,000 chance that you're going to have a collision. So it's proportional to how full the table is. So a good hash function should be relatively simple and efficient to implement. If it takes big O of n to calculate your hash, you're wasting your time, because you could do a linear search through the keys and find it in big O of n time. So your hash function needs to be quick. It can't be if it's n squared, then it's even worse. It takes longer to calculate the hash than it would do a linear search. So you want to use a simple hash algorithm, and a multiplying by a prime that we showed you previously is a quick operation. It's not dependent on the number of keys you have. It's dependent on the length of each key, which is not a big O of n. It's big O of 1 operation. Now that we've got a hash and we've got an index into our table, how do we deal with collisions? Well, there's two primary ways of dealing with collisions. One is called open addressing and probing. The second is called chaining. In open address and probing, the word probing gives you a hint as that when we have a collision, we're going to probe or try to find the next open spot in our table. Chaining gives you an idea that we're going to create chains or linked lists of the items at that index. So let's talk first about open addressing and linear probing. So we're going to go step by step. So the idea is that if the item in the table at the index calculated for the key has the key, we found the item. So we say, what's the index we want to be at? We look at the item there. If it has the same key as the item that we're trying to stick in, then we found the item, it's there, we say yes, we return it. If that item has a different key, so that means something's there, we had a collision, then we increment the index by 1 and look at the next space. And if we check to see, is that null? If that's null, then the thing's not in the table. Or if it's got the right key, then we say that thing's there. If it's got the wrong key, we keep incrementing the key, modding by the table size, so it's a circular array. And we say we find the key, so it's in the table, or we find null, which means the item we're looking for is not in the table. So the algorithm is basically you compute the index, which is again math takes absolute value of the item's hash code, mod it by the table length, that's the index. If the table at index is null, the item's not there. If the table at index is equal to the item, then it's that we found it. Else, we continue to increment the index and compare the table at new index to see if it's there, or if we find a null, then it's not in the table. So we're going to linearly probe through the table rounding. So let's do an example of linear probing. We want to put Tom, Dick, Harry, Sam, and Pete into our table. We want to put 5 things into our table, which is 5, so we're going to have lots of collisions by the end. Not a very efficient way of doing things, but we'll do it. So we take Tom, its hash code is 84,274, mod by 5, and the result is 4. So we go and want to put Tom at position 4. There's nothing there, we stick it in. We then take Dick, we take the hash code, and we want to put it in 4, but 4 is something's there, so we increment the index, mod by table size, which puts it at 0, and so we put Dick at 0. We take Harry, the index is 3, there's nothing there, so we can put it in there. Sam's got an index of 4, which collides with Tom, we increment, collides with Dick, and then we can put it in at 1. And now Pete goes with 3, so he collides with Harry, collides with Tom, collides with Dick, collides with Sam, and we can insert it. Now the retrieval of Harry and Tom takes a big O of 1 because they're at their index. The retrieval of the other 3 people has a linear search, because you're going to have to probe, because you're going to say, oh, I want to see Pete, but I see Harry. No, I probe, I see Tom. No, I see Dick. No, I see Sam. Oh, I finally get to Pete. That's a linear search. That's big O of n, actually, because I had to go all the way through my table. So that's not very efficient because of the collisions. Now, because the table size was small, let's increase the table size to 10 and see what happens with the same set of people being inserted into the hash table. Actually, hash table size of 11. You should always choose a table size that is a prime number. It gives you better hashing. You get better distribution of your hash codes when you mod by a prime number. So we put in Tom at 3. Dick is now 5. Harry, which used to collide with Tom, now doesn't at 10. But Sam does collide with Dick now, but we can increment by 1, so that's very simple. And then Pete goes in at 7. There's no collision. So the best way to reduce the possibility of collision and reduce the linear search is to increase the table size. The issue with increasing the table size is we now have 6 extra spaces in the table that are empty now, whereas in the previous example we filled the table. So you're trading a little space for reducing the collisions. So you increase the space, a little bit of wasted space, but you have much better performance. These are all basically big O of 1, except for when you have to look up Sam. You look up Sam, you're going to say, oh, it's at 5. No, 1 more, I found it. And the probing will be short, hopefully. So we can now see how we can add to the table. How do we delete an item out of the hash table? Well, if we're losing open addressing and probing, you can't just delete the item from the table, because what if in the previous example, I think it was Harry was the collision. If you remove Harry and you say, where's Sam? Well, it's not at the place. You say it should be there, it's not there, but we linear probe past it. So we can't delete the item from it. We need to mark it as deleted, or make a dummy item indicating that it is available so we can insert a new guy in there. But if we're searching for somebody, we need to do our linear probing past it. And you cannot replace the dummy item with a new item until you check to see if the item's in the table, because if you put in Harry, you delete Harry, you put in Harry, and you put in Sam, and it probes, and then you say, oh, I want to insert Sam again, you can't put Sam in the place where it had the collision because it's already in the table. So you don't want to add the item twice. So it does cause a little bit of issue when you're doing insertion into the table after it's been deleted. You have to check to see that it's not in the table. Again, like I said earlier, we want to expand the table size as the number of items in the hash grows because we want to keep the load factor low. Using prime numbers for table size gives you better performance on the modding by the table size, gives you a better distribution. Fuller tables lead to more collisions, as we showed, because you're going to hit something and then it's likely the next item will be there. So you, when you get sufficiently full, whatever your comfort level is or your performance level, you want to increase the table size, just like our reallocate for our array-based lists and queues and all that stuff. So we create a larger table. We rehash those values, everything in the table, into the new table because we got a new hash, table size. We need to recalculate what their indexes are, and we don't insert deleted items because they've been deleted, so we don't have to worry about deleted items. So that sort of redistributes the items in the hash table into our new table, and that's how we do it. So that's how we do for linear probing. Another solution with open addressing is to use the concept of quadratic probing. The issue with linear probing is if you hit a collision, the next spot's going to be where we look for our next thing. So if we can get chains or clusters of keys to collide. What quadratic probing is instead of adding 1 each time to our index, we're going to add a larger and larger and larger value to our index. So we sort of hop or jump over things, and because we're modding by the table length, we are we'll wrap again, so we tend to not have as many clusters. So what we would do is say increment the index by 1 and then 4 and then 6 or 9, excuse me, by doing the quadratic equation for how to increment our index. The equation is we can increment the probe number. Our index is now the start index plus the probe number squared, mod by the table length. And so we would tend to look, for example, if our hash code was 5, the first probe after a collision would be at 6, and then at 9, and then at 14, and then 21, and then we mod by the table length to see where we end up back into the table. And that, as you can see, the space between the probes is getting larger, so there's less chance of getting those long blocks or those long clusters of collisions. One of the issues is that this calculating of the next index is now time consuming because we got an additional mod and additional multiplication, so that's making our calculation of the index a little bit slower. So another way is to take a value, k, started at -1. Every time through we increment it by 2, and then we take the index and we just take this k and add it to it, and it gives you a very similar progression of probes that the other one, which was a little more expensive. So it's a little bit quicker algorithm to give you a similar quadratic probing profile. One issue, though, with quadratic probing is you may, because of the way the quadratic probes grow and grow and grow, you may not hit every spot in the table. You can get these patterns of you jumped over a space and that space is never going to be used when you're searching to say, is this item in the table? Because the probing cycle could cause you to have this hitting the same things again and again and again, which might lead to an infinite loop because you don't know you're just hitting these items again and again. You never find null in the search, so you keep going. If the table size is a prime and the table is less than half full, you won't have this infinite loop because you're going to get something. But then problem with that is you can't have a load factor of greater than 0.5. You half full. So that is an issue. I mean, you're wasting a bunch of space to guarantee that your quadratic probing won't cause infinite loops. But it does reduce the collision length of the clusters. So you have to make a choice of wasting space or not. So an alternative to using open addressing and probing is to use chaining. Each element is not the item, but it's a head, or it's a head of a linked list. So when you have a collision, you just add the item to the linked list after checking to see that the item's not in the linked list. This is often called bucket hashing because each item in the table is now a bucket that holds things. Sometimes it's called bucket hashing. You now can store more items in your table than the table size. Once you have your index, you only need to search the items in that linked list. So that's quick. You can store more items than the table size. As I said before, you could have long linked lists hanging off the table. Once the item is not in a bucket, you search the thing, you can then add the item to the bucket when you're doing insertion. To remove an item, you don't have to mark it as deleted, you don't have to do anything, you just take it out of the linked list and it's no longer in the hash table. So there's none of that, oh, we gotta worry about whether it's there or not. You don't have to resize your hash table. You probably want to if your linked lists get very long, because now you're doing a big O of N search through the linked list, but so it's not that bad, so you may want to resize it, but you don't have to resize it quite as often as you did in the open addressing and probing example. So what's the key term for the performance of hash tables? It's called the load factor, the number of filled cells divided by the table size, right? So in open addressing, each cell that has an item is filled. Load factor has the greatest effect on hash table performance. Lower load factor is better than high load factor because there will be fewer collisions in the open addressing model, or collisions as in you'll have long linked lists. If there are no collisions, their performance for search and retrieval is big O of 1 because we take the hash code and there it is. So that's the goal. We want to reduce the number of collisions, so we need to look at what is sort of the number of comparisons we need. And so Dr. Knuth came up with this idea of, he calculated how many comparisons you need based upon the load factor. For open addressing and linear probing, the number of comparisons to find the item is 1/2 times 1 plus 1 divided by 1 minus the load factor. And in chaining, it's basically 1 plus the load factor over 2, because the load factor is basically going to give you the average length of your linked lists. It's the average time it takes to search your linked list. So here's a table that shows us the number of probes or the number of comparisons. Average time is going to take probes or comparisons for a linear probing or chaining. As you see, the load factor, if it gets to 0.95 in linear probing, we have lots. We're going to do a lot of bouncing around because we're going to hit those collisions. If the table's full, we're going to have a lot of probing. Where in chaining, we have much less because, again, it's just searching the linked lists. Now we can compare this to storing the data in a binary tree. If we're sorting, we store the array of 128 items. In a binary tree, that takes 7 probes, which basically means that unless your load factor is 0.9, using a hash table, even linear probing, using a hash table is more efficient than storing it in a binary tree. So if you keep your load factor around 0.75, you're going to have an efficient, very close to big O of 1 algorithm for storing things. So again, back to the binary search tree versus using a hash table to store your items. Hash table getting thing is big O of 1. Worst case, again, very worst case, is big O of n, because you're going to either have to do the probing through all the things in the table, or you're going to have to search a big long linked list. Unsorted array, again, linear search, big O of n. Binary search tree is going to be log n if the tree is well built. If it's badly built, again, that's a linked list, big O of n. So the performance of a hash table is superior if the load factor is less than 0.75. However, you pay the price with empty storage, so you're sort of wasting space. You're using up more memory. So let's talk about some of the storage requirements for these things. A sorted array or an unsorted array. There's no empty space because we have n items in the n length array. Binary search tree, there's no empty space because each node has something in it, and if it's balanced, we got 3n references. We have a reference to the data, we have a reference to the left, we have a reference to right, subchild. Open addressing, we keep the load factor at 0.75, so we need a third more space to have than the references. And then in chaining, we have m entries in the table plus 2 times the load factor references, so that actually is the number of items. So for each item we have 2 references, the head, the point, and back, plus we have space for the table. So example, if we wanted to store 60,000 items in our table, we use open addressing that says that we need to have a table size of 80,000, and that will take 2.5 probes. So in chaining, the number of comparisons is the load factors divided by 2, and so we want to have 2.5 probes, so that it will help us determine how many items we want in our table. So we just multiply this by 2, so we get 5 plus 2L, and that's the load factor. So the load factor is 3. So now we want to calculate how big the table needs to be. So we divide the number of entries by 60,000 by m, that's the size of the table needs to be 3. So the table size needs to be 20,000 entries, which is a fourth the size of our open address table, which would give us the same number of probes to get to our items. So we saved a lot of space there. And so the storage is basically the 20,000 entries plus, or the 20,000 table size plus 2 references per every item. So we have 140 references. Whereas the table size, the other one, we have 80, we had to make it larger. So it takes a little more space because of the additional references, but not much. And so that's this brief summary of hash tables. We can calculate the load factor, which we want to keep less than 75%, or for open addressing or for chaining, we can calculate the size of the table that gives us the same number of probes. So hash tables are a very good data structure if you want quick access to the items in the table. It does take a little more calculation of, you got to take the hash code, get the index, do the thing, decide whether you're doing linear probing or chaining, but a very efficient data structure for getting access to data quickly. Thank you very much.